Well, it's a pleasure to be here tonight. I want to thank Dean O'Donnell and the college for inviting me here. It is another great opportunity for the laboratory over in the east side of the state to work with the University of Washington on issues of national consequence. I must say that people from the eastern side of the state usually feel a little uncomfortable being surrounded by this many Huskies all at once. So I'm looking forward to tonight. The dean asked me to share my perspectives on the role that electric power system is going to play, specifically the smart grid, in our emerging energy challenges in the United States. I chose the word challenge instead of crisis. We always have varying degrees of challenges, and we are facing some special challenges both as a nation and also as a member of the global community. I believe that we are poised at the threshold of a substantial global journey as we look to the energy future of our global community over the next 20 to 50 years. Tom Friedman, I think, from the New York Times framed it well. He framed the challenge as decarbonizing our energy economy in a way that maintains our economic vitality and competitiveness. He framed that as a challenge that we're going to face for the next generation. And I think that regardless of the ultimate decisions that we as a nation make regarding carbon, energy security, environmental stewardship, it's clear that our reliance for our economy, our increasingly digital economy, we are much more reliant now than we were even 20 years ago on clean, reliable electric power, and that reliance for our digital economy is going to increase rapidly over the next several decades. So in my comments tonight, I'd like to make a couple points, and I'll let you be the judge on whether I'm able to make my case or not. First, the power system, which for many of us, for most Americans, it's that invisible entity on the other side of the wall plug. That power system is going to change more in the next 10 years than it's changed in the last 80 to 100 years. And I would argue that in the next 10 years, you as consumers, whether it's your industry, your company, your business, or your home, are going to be much more engaged in that grid. You'll have the ability to interact in two ways, communications, and you'll have the opportunity to make choices that will be a benefit both to you as well as to national public goods or national issues that we face. Number two, because the grid's going to be asked to do more in the future than it has been in the past, the grid will become more strategic and increasingly central not only to your local needs for affordable clean power, but for solving some of the nation's tough challenges, whether it's energy, environment, or security. Number three, I believe this transformation will require our best assets in science and technology, but probably even more fundamental, the human sciences and policy, because of the scope and the scale and the complexity of the power system, of the energy economy to which it will become increasingly central, and to the increasing complexity of our global economy are going to require the best of the assets that we can bring to bear, like people like Shwetak and some of his colleagues here in the university. And then number four, prevalent throughout all of this, information technology and related concepts will substantially transform our grid and energy economy in general, not unlike what the internet did for e-commerce just over the last 10 or 15 years. Just think how recently, we just passed the anniversary of the internet, and it's not been that many years. And just think how fundamentally transformed our e-commerce economy is. And as we did in the internet transformation, the universities and businesses and government bodies in the Pacific Northwest have a lot at stake in this transformation. But these same entities in the Northwest also have a lot to offer in terms of leadership. And that's what I want to try to share with you tonight in terms of where I think we in the Northwest fit into that picture. So let's start by looking at the power system that we have today. It's amazing that it's only been with us about 120, 130 years. Started in New York City as a small local community power system. It grew service territory by service territory. such that today it's been a fundamental element of our overall economic vitality for the last 120 years. Its focus has been pretty simple. It's had two basic metrics: affordable power and reliable power. Historically, the first major change that our grid saw occurred back in the Great Depression, at which time substantial federal investments were made to put people back to work that led to the rural electrification. And I have to say that my grandfather at one point ran the rural electric administration back in the 50s, so I come by this honestly. And that really was a major step change in terms of the electric power system in our economy. The next big change was the emergence of the regional power exchanges, which happened in the 50s and 60s as the nation sought to respond to the economic growth in the post-war economy. And this was the point at which we began to feel that it was important, or there was economic benefit for moving power not just locally, but across major regional exchanges in the Northwest down to California, and the upper Midwest down eastward into the big load centers in the east, et cetera. So it was in the 50s and 60s when that big change came. We quit being local and began moving power over long distances. Today, the North American power system is hailed as one of the great engineering feats of the 20th century. And it's delivered exceptional performance. And I have to say, I fought the phrase smart grid, because I know we've been using computers and intelligent devices for the last 15 or 20 years, at least in the transmission system. But I also have to say, there are utilities today in the United States who wait for a phone call to find out if there's an outage somewhere in their distribution system. So today we face some big challenges. Let me try to frame for you the complexity of the system. First, in this country, we have over 3,500 utilities of all different business models and regulatory regimens, and about another 3,000 or 4,000 merchant generators who provide power onto that system, whether they're independent generators or perhaps large industrial firms that provide power. Totally, we have almost 20,000 generators across the country. We have over 150,000 miles just of the high voltage transmission lines, and these are lines that today require about 7 to 15 years to permit, fund, and build. And out of that 150,000, we're probably going to need to add another 50,000, or roughly 33% more, to try to capture a lot of the clean power, like renewables, and move them to load centers. So it's one thing to stand up in tower and string cable, but you got to get the capital, but tougher yet, you got to get the permitting and siting. And this is at a time when we're running up significant federal deficits and other economic challenges that we face, so we need to be as careful and prudent in these investments as we can be. Number three, we operate 3 interconnections. We have 3 big electrical machines in the United States. The Western interconnection runs from British Columbia down to northern Mexico, California, over into Nebraska. Texas, who here is from Texas tonight? Well, Texas likes to do things the Texas way, so they drew their boundary just inside their border. The Eastern interconnection is everybody else. And Quebec, if you count Quebec, because they do pump a lot of power down into New England, Quebec likes to do things the Quebec way as well. So we have, each of these are large electrical machines, and the challenge of that machine is you have to always maintain perfect balance between supply and demand with a commodity that moves just under the speed of light, and that's really tough. And most people don't realize the complexity of what goes on the other side of that wall plug to keep that whole system up and operating. To model one of these interconnections, like the Western interconnection, you have to model about 30 to 40,000 electrical buses on that system. Add on a couple, 3,000 or 4,000 generators. For each generator, you have about 8 couple differential equations that you have to monitor in real time. And in terms of real time, we're talking milliseconds, because the grid can go south on you very quickly if it gets out of balance. So these are incredibly large, complex analytical problems, and it's led to a couple archaic characteristics of our system. Most of the state estimators and other things we use to determine is our system safe, is it between the white lines, typically take 3 to 5 to 7 minutes. So it's like driving, looking in the rearview mirror. When that model converges, you know, okay, 3 to 5 minutes ago we were in a secure regimen. That's not real time. The nice news is information is going to give us a chance to make that more near real time. In the 1990s, we had some policy changes in the United States. We deregulated natural gas, and actually it led to much greater efficiency in the markets, and it was a very positive experiment. So then we wanted to go to electricity. Well, again, it's a little different commodity, moves a little faster, a little tougher to store, and it created some uncertainty. So in the 1990s, the investment in our infrastructure nationally started to drop off, both generation and transmission. We used to have a cushion of about 25% that let us kind of ride through the little potholes we encountered along the way. Well, when they stopped investing, that reserve margin decreased down to 20%, 18%, sometimes to 15% in certain parts of the country. And that's why you hear more tidbits on the news about tough days in Southern California and tough days in New York when they're having to send out stage 2 alerts and ask people to back off on the power, because we lowered our investment and we had to operate closer to the edge. Then, of course, there have been several major blackouts in the last several years. Let's talk about that. The blackout in 2003, we talked to the head of the New York ISO just that day, and he was talking about how easy the summer had been. And then he had 2,000 megawatts that reverse flow around the Great Lakes and tried to sneak in his back door and dropped a good fraction of New York and New England. And that outage cost $6 billion in lost economic impact. Estimate nationally in terms of just poor power quality and other things, it's about an $8 to $10 billion cost annually for us as an economy. So these are big numbers. It's a big system, very complex, and very expensive when things get outside the white lines. In 2005 and 2007, 2 major pieces of energy legislation began to try to right some of these challenges. They provided the right sort of incentives to get investment back going again in transmission, and that's doing well. And in 2007, the notion of smart grid was unveiled in Title 13 of the Energy Independence and Security Act. A lot of support from our regional delegation. Senator Cantwell was one of the leading innovators in terms of the smart grid legislation. And these policy changes, combined with the underlying revolution in information technology, bring to us a very exciting convergence of opportunity in terms of transformation of the power system and what we can do to help transform that system. So let's look at where our nation's grid is heading. Just very quickly, first, under business as usual, we're likely to have demand double by 2050. And why is that? Because our economy is becoming more and more digital and reliant on clean power. So that's just business as usual. It would take us about $80 to $150 billion to make the upgrades in the infrastructure to meet that. And that doesn't deal with issues around carbon or carbon taxes or other things. That's just modernizing the old-fashioned way. But in addition to meeting this demand growth efficiently and reliably, the nation is now putting new expectations on the grid that it did not historically have. We're calling for roughly 20% renewable generation by 2050. The Pacific Northwest is a leader in this effort, and it is unbelievable to drive down the Columbia Gorge or to Ellensburg now and see what's transformed in terms of wind generation just here in the Northwest in the last several years. We're at about 2,000 megawatts, which is like 2 nuclear plants worth now, and Bonneville's pushing towards about 4,000 to 6,000 megawatts. That's a substantial investment, and that's bringing a lot of challenges to how we operate the grid in the Northwest. Energy efficiency is the lowest hanging fruit. It's the best option we have for improving the efficiency of our energy system and dealing with things like carbon issues, if indeed we move towards some carbon policy in the next 1 or 2 Congresses. And the smart grid and the intelligence in the system offer substantial potential to help measure and verify what's going on there, to help close carbon markets and other things, if indeed we move our policy in that direction. Thirdly, there's much discussion around plug-in hybrid electric vehicles, both here in the Northwest and elsewhere. Some of the initial studies looking at the power system and asked the question, how much of the light-duty transportation, that's cars and small trucks, could our existing generators and existing wires handle if we just manage the charging so they don't overload it during peak times? How much of that transportation load could they handle? The upper limit's about 70% of our national light-duty transportation. That's significant. That would equal about 50% of our imported oil. So from a national policy perspective, I'm reducing our balance of payments and energy security. Electrifying transportation offers some significant degrees of freedom that we as a nation are looking at pretty seriously. Electric generation is a major contributor to carbon emissions in the U.S. It's about half of our power comes from coal. China fires up 1 new 1,000 megawatt coal plant roughly a week. And they're actually being as aggressive as we are in terms of renewable energy and other things. But their economic growth is so strong that their addition for carbon generation is moving very quickly. Finally, digital communications through the power system bring with it also the challenge of cybersecurity, and how do we deal with privacy and cybersecurity. So, as if that doesn't make things tough enough, let's look at what else is going on. The target is moving on us. Today, and for the last 80 years, our system has pretty much had a once every 6 seconds look at where it's at. We have very little intermittent generation. Pretty much all of it is big, predictable generation. Lots of electromechanical inertia in the central generation. Almost no price responsive demand. Most people don't get a price signal. They just plug it in and get it when they want it. Most of the end uses are pretty simple, and we have virtually none of our transportation covered by electricity. I think within 10 years, you're going to see the emergence of a new monitoring system that's well underway right now, where instead of once every 6 seconds, we'll be able to take a time shot of the system 30 to 60 times every second and put a GPS timestamp on it to give us, it's like going from X-ray to MRI in terms of a very rich awareness of what's going on in the system. More than 15% of our generation will be intermittent renewables. We'll also have a lot of distributed generation and demand response, so that'll be different from the central generation. Probably more than 15%, probably 20% of end uses will be able to get a price signal, and that'll give people a chance to engage and help support and respond to the real-time price of power. We're going to have, when we monetize carbon, we're going to push efficiency in this country like you've never seen it push before. And you're going to see a lot of new loads, power electronics like LED lights and other things that will dramatically change how the loads behave. And I think you'll see a lot of transportation get put on. So my point here is we can't design solutions for today's grid, because this grid is going to change dramatically, more in the next 10 years than it has in the last 80. All right, so Dean O'Donnell asked me to frame a few thoughts in terms of, so what are our choices? How do we go about solving some of these things? I would highlight, number one, if we have the ability to look at the system 30 to 60 times a second, and then have smart meters to provide two-way communications to the consumer's home, we have the opportunity to fully leverage that new information technology to see this system with transparency like we've never seen it before. With high precision, do it in real time. It'll help us improve reliability, squeeze more out of the existing assets, and optimally expand and operate our system for economic and energy efficiency. And when I talk about asset utilization, the big transmission line that goes from the Northwest to California, it's rated at 4,500 megawatts. That's 4.5 nuclear plants worth. Its thermal upper limit is 7,000 megawatts. We're leaving 2.5 nuclear plant equivalent of capacity lightly used on that line because we can't see the system in real time, so we rate it very conservatively. If we, with new information technologies in real time, can see it in real time, we'll be able to uprate that line to get a lot more economic productivity out of that transmission line. That's just one small example. So I mentioned phasers, going from one every 6 seconds to 30 to 60 times a second. Smart meters, you've heard about them. In our demonstration on the Limerick Peninsula, we went from 1 data point a month to where we were getting 9,000 data points a day from each residence. And that gives you resolution to really understand how to optimize voltage and other things at that end use. I think number two, we need to improve the cost and performance of energy storage. If our new future system is going to be very dynamic, two-way, and complex, we need more degrees of freedom for operating that system. It's a simple optimization problem. Energy storage is something we don't have very effectively today. We have a little pumped hydro. We need to get the price point down to $1,000 a kilowatt installed. It's about $2,500 right now. That's a major basic science challenge. And we also need to get the advanced communications and controls to take advantage of it. Number three, we need to add demand to how we operate the grid. For the last 100 years, we've operated it strictly from the supply side, using an accelerator on the generators to handle increases and decreases in load. If we can capture demand and you work it simultaneously with the supply side, I think that we can reduce the investment in the future by about 30% for the future demand growth. And a lot of the services that we need to keep the grid stable, we can provide from demand. It'll be cheaper, greener, and faster. We need to transform our approach to cybersecurity to build cybersecurity as an inherent part of the control and communication systems. Today, it's not inherent, and we're doing too much band-aiding and patching kind of after the fact. And once we get these four cornerstones in place, we will then have the wherewithal to push renewables well past the 20% level if we so choose to. And we will be able to deliver new analytic tools that will take us to levels of resolution and understanding and control that we've never even dreamed possible. So let's talk about smart grid. It's a phrase I tried to avoid because we have used computers and other things in parts of the grid for many years. But smart grid basically means three things. It's sensing, two-way communications, and control, ubiquitous throughout the power system, including down into the end uses, and Shwetak will talk about that later this evening. And it's basically not only getting that communication flowing, but extracting value from that and operating the system in different ways than we have historically. That's both at the demand side, and it's also up at the transmission side. So let me offer a process that I think is important. Smart grid is a means to an end. It's not the end in of itself. And when I think of smart grid, I think the process really should go like this. The simple proposition is to leverage rich data like we've never had before, to provide new knowledge and understanding of systems, how they operate. That's looking at both the physical, the human, and the economic dimensions of those systems, and use that to substantially improve the efficiency, economic efficiency, and energy efficiency of our energy economy. And then based on this new knowledge, create a whole new fleet of next generation tools that'll let us operate that system more effectively, and most importantly, help us as a nation deliver those important outcomes that are on our horizon today. Outcomes, outcomes, outcomes. Historically, we only focused on affordable and reliable, but I think going forward, the power system is going to be the means to deliver a lot of the outcomes we have in security, economic vitality, and environmental stewardship. So it's really going to be a totally different game, I believe, going forward. Phaser networks, I've talked about this a little bit already, but we are in the process of trying to get networks across the United States. In the Eastern Interconnection, we just crossed the 100 devices point that are networked and communicating. That's 30 to 60 samples every second, and making that data available to operators across the interconnection. So the next time Ohio starts to struggle, New York will see it and start to play defense. Same with Tennessee, same with those around them. The West started this journey with Bonneville working back in the 90s. They were the first ones to implement phasers. We supported them in that process. They're at 100 devices now. What's exciting about the recent grant announcements for the stimulus package, the Western Interconnection submitted and was awarded a grant to put in another 250 phasers over the next 18 months. So within 18 months, we will have the ability to see the Western system like it's never been seen before and deliver next generation tools that will give us much higher levels of reliability, throughput on some of the key transmission lines, et cetera. It's a transformative moment. The Eastern Interconnection is going to get to about 500 devices based upon some of the grant investments. I think it would have taken us about 10 years to do that under the previous approach. So it's basically a big acceleration of getting some of that fundamental infrastructure in at the transmission level. Texas is doing pretty well. I mentioned earlier this issue of you get data and they'll deliver new knowledge. Texas lit up their first 4 phaser measurement units last fall. And in the first week, they found 3 dynamic or oscillatory anomalies that they had no clue was there underneath their system and was making them vulnerable. So again, it's like going from an X-ray to an MRI, new discovery, new knowledge. Now what do you do? It gives them much more power. Here are some of the tools that we're developing at the laboratory. Top left, I know that's kind of an eye chart. But in '96, the Western system had a small signal oscillation that took the system down. It was not damped. To calculate how much that damping ratio was took about 7 or 8 minutes in 1996. Today in our lab, we have a demonstration that's moving into control rooms that uses phaser data, calculates that damping ratio in about 1/3 of a second. And if the operators had had that system in '96, they would have had about 5 or 6 minutes of recognition that we were just about to lose the Western system. On the top right is a wide area entire view of the power system in the Eastern Interconnection, leveraging some of their phaser data. That's the first view that operators have in the Eastern Interconnection to see the entire health of the Eastern Interconnection at the same time. Today, most operators see only their company footprint. So that's where we're trying to go with smart grid technology. The bottom right is leveraging some national security visualization tools we had. We told them we had a big problem. We got 60,000 buses in the West, and we want to bring in 30 samples per second and look at it. And they told us that was really a pretty small problem. And what they did is they changed it from a geographic layout to one that looks like the impedance. It's what the Western system looks like to an electron. So that's a time-stamp picture of the Western system from an impedance standpoint. And each of these narrow points where it gets narrow, those are areas where the system would naturally island if it were to fail at that point in time. This gives operators a very profoundly more powerful ability to see what's going on in real time in the system and identify where they need to work to keep the system up. So here's one of my favorite pictures, and this is the outage in 2003. This shows two parts of the Eastern Interconnection, Western Michigan, and this is Cleveland. Now, I won't make any Cleveland jokes. Some people say, when in doubt in the Eastern Interconnection, the first thing you do is you drop Cleveland. That's not true. But if they had had then the phasor measurement system, it would have shown about an hour and 40 minutes of time where Cleveland was clearly pulling away electrically from the rest of the system. And that pulling away, that change in phase angle reference, indicates stress on the system. That's a lot of time to play defense. They probably could have either avoided the outage or substantially reduced the scope of the outage and substantially speeded up the recovery of the outage. And again, it's just information delivered and used at the right time. That's all that is. So we had some fun in the Pacific Northwest here. Senator Murray and others helped get, I think really, it is still the poster child for smart grid demonstration in the nation, where we set out to do an economic experiment. I know that's heresy in an engineering college, but it was an economic experiment to say, look, will consumers sign up for real-time prices? Will they care about the information they can get from a smart grid? What would they do with it? We wired electric water heaters, the HVAC system, and dryers. We tried out a couple different devices, but the key thing was we gave them a price signal. We made it easy for them to respond to that. We basically gave them a slider switch. We said, you can choose to be either really green or really comfortable. You set the switch where you want it. We'll give you a red button to override it for 24 hours if you're having a party at your house and you just don't want to play. But we got to tell you, the more you go towards green, the more money you're going to get back every 2 months when we send you a check as a rebate for letting your house participate and help support the grid. And we send a real-time incentive signal or price signal every 5 minutes from the laboratory to them via the internet. So that was the experiment. And we also told them that at worst you'll pay your regular utility bills, but at best you'll have a chance to save some money. So here's what we learned. We gave them some incentives to back off a little bit when the system was struggling. And we found that over the course of a year, they reduced the load on a distribution feeder by an average about 15% of the peak load. That means money in the pockets to consumers and utilities to help avoid upgrades to distribution systems in places like Seattle, where that's very expensive. We also found during a 3-day winter storm, much like you sort of had last night, a little warm up for the winter season here, we drove strong incentives to drive the prices up to encourage people to back off a little bit. At most, it was about 1.5 degrees, 2 degrees difference. And we held those feeders down at 50% of the level, which shows the ability of an incentive signal to get people to orchestrate and work together to help a system ride through a windstorm without outages. Overall, people saved about 10% on their bills. And, you know, they wanted to get a little action. They wanted to have some fun. But the money wasn't the big thing. The big and the post reviews with the consumers really wanted to be part of the activity, have a choice, get a little benefit from it, but also contribute to the greater good. And over 95% of the people, this is in a state that's not a deregulated state. We don't have real-time prices in the state. Over 95% of the people said that they would very likely participate in something like this in the future. And we have a demonstration that we'll talk to you about here in just a minute. This is it. We worked with the University of Washington and Bonneville and many others. We've submitted about a $180 million proposal. We hear it's going to get announced on Thursday. We're feeling very lucky. I wear my baseball hat inside out, my rally cap every night. But I'm feeling lucky. But we worked with about 12 utilities in the region, as well as Bonneville, to frame investments in smart grid both at their local area, but then set up a regional incentive system, a message or incentive signal, that would extract over 100 megawatts of that responsive smart grid devices out in the system to respond to regional interest, whether it's transmission congestion, whether it's the need for ancillary services to help with renewables integration, whether it's the need to reduce capacity, to reduce some of the Columbia dams from putting too much dissolved gas in the water and killing salmon. In other words, use information to help coordinate the behavior of these smart grid components at the local level to help serve some regional benefits and interest. Last point I'd like to make, smart grid, carbon. Is there a connection? We did a bounding study. We just completed it. The report's not actually finalized, but it's been presented back in DC. And we looked at if you had full penetration of the smart grid in the country, what are the connections to smart grid and carbon management? And we found that sort of at the upper limit, it's roughly about a 12% potential reduction in energy consumption with smart grid. And here's some of the key components. The easy putt, 3 to 5% of demand goes down just when people are aware of energy, what the prices are, and what the use patterns are. Just that awareness has a strong conservation effect. We've seen it very strongly in commercial settings. It's now emerging in residential settings. We don't know how durable that effect is, and that's one of the remaining questions we need to answer. We've also identified for plug-in hybrid electric vehicles, there's substantial savings in terms of total energy use because centralized generation of that power is more fundamentally thermodynamically efficient than all the individual small engines out consuming fossil fuels to deliver transportation. There are also some emissions benefits. So to a large extent, there's some strong energy efficiency benefits from electrifying certain portions of transportation. One of the more fascinating dimensions is this whole issue of building diagnostics and commissioning. Almost 50% of the big commercial buildings in this country go outside of their design spec from an efficiency standpoint within the first 3 years. And most building owners and occupants don't have any ability to know that devices are out not running, they're broken, certain inlet air vents and sensors have gone bad. And so the use of diagnostics connected to the smart grid efforts could dramatically improve the efficiency of just end use throughout the residential and commercial side. And you're going to hear Shwetak talk about that a little bit as well tonight. So other studies have pointed around 7%. We set an upper limit at about 12%. There is going to be a strong connection between smart grid and carbon policy and energy efficiency. So again, this is an example where grid, which historically has been invisible, just that thing on the other side of the wall plug that you took for granted, it's going to play an increasingly strategic role in everything that you guys do and we as a nation try to tackle in terms of our national policies. So let me close very quickly. The system has to expand. And that's tough. We have a hard time siting and permitting new activities, but demand is going to grow regardless of what we do in terms of efficiency and carbon because our economy is getting increasingly digital. We are going to be asking the grid to do many new things that it was not initially designed for, so the grid's going to have to change. I think it will be very central to not only the traditional values of affordability and reliability, but many public policy issues that emerge for us as a nation. I think it offers great opportunities not only for us to improve what we do, but also help position us in an innovative standpoint for new products and services to take elsewhere around the world. China's ahead of us right now in a phaser measurement network, but we're still ahead of them in understanding how to take advantage of that information and deliver new value from it. And that's an innovative edge that we need to keep. And lastly, it's a great opportunity for not only the workforce of today, folks who are still in industry and business, but also the students and the professors who are working with them. I think the UW and other academic institutions, both here in the Northwest and around the country, have an amazing opportunity. And I have to tell you, the power engineering graduate courses I've been going to talking to are really ticking up. I mean, the students are getting the word, lots of excitement out there. Big transformation at the national level. And now I'm very excited to hear what Shwetak has in terms of bringing the helicopter down a little bit lower and talking about the demand side. Shwetak.
Thanks, Carl. So what I'm going to talk about now is looking at things that are a little closer to home. How can you make a difference? How can we make a difference? And something that we can actually get a head around that's in our own home. So I'm going to be talking about some research that our lab's been doing. In particular, this is collaborations with Dr. James Landay and James Fogarty. So I don't do it by myself. We have a lot of great faculty that I collaborate with in our department. And so what I'm going to be talking about is how to make the grid in our home smarter. So the invisible wall behind us, the electricity, well, how do we make that more visible? How do we take advantage of that and look at, well, what is this thing that's behind our walls? And how do we take that information and make some interesting decisions about it? And in the context of helping us reduce residential consumption. And so there's a big disconnect about how much electricity, water, or gas you consume with what you're given back as feedback. And so the talk is going to be in the context of energy in general, electricity, water, and gas. So I like to always start with this analogy of something that we are pretty familiar with, which is grocery store shopping. So let's say we're shopping at the grocery store. Everything's labeled nicely. You have prices for everything. And so after you check out, what do you get? You get this great bill, itemized bill, that tells you exactly what you purchased, how much you purchased, And now, Safeway offers this really great feature where they kind of categorize what you've purchased. Baked goods, grocery, refrigerated items. So now you get a better sense of what kinds of things you've bought. If you see the bill being a little high, you can actually kind of decompose it down and start to figure out, well, where do we spend too much this time? But you get a lot of good feedback here. But what if Safeway didn't give you that? What if Safeway gave you this, which is, okay, you bought about 1,000 items, and you owe us $500, right? So we would be in uproar if we didn't get an itemized receipt. And just think about your telephone bill. Think about your credit card bill. If you didn't have an itemized bill, just think of how we would respond to that, right? But it turns out that our electricity, water, and gas bills are not itemized. They're aggregate numbers, very similar to the scenario of the Safeway bill. All right, so this is actually an example on the left, is an electric bill from one of my colleagues in computer science, which is a $3,000 water bill that he got just 2 months ago. And what did he get? $3,000 is what you owe, and you consumed over 120,000 gallons, right? And so there's this big disconnect of exactly what did he consume and why does he owe $3,000? It turned out that his sprinkler system actually leaked that summer, and he didn't know that had happened. And I'll talk a little bit about this later because we could actually figure out that this was going to happen before it even happened. But if he had an itemized bill, he would actually know where that particular leak happened or where the water was being consumed. But now what we have is just an aggregate number. You consumed 1,000 kilowatt hours this month. Here's how much you owe us. Thank you very much. So what if we had more information than we have now? In other communities, we're seeing a trend of giving you better feedback. So if you go buy a car, the EPA does a great job of giving you some information about the efficiency of your car. And you can actually use the interface in your car to help you figure out, well, how are you meeting that goal? How are you driving? Can you change your driving habits to meet that efficiency rating? And just give you some feedback about how you're doing. Changing your driving habits so that you can actually be more efficient. So feedback actually can play a really important role for helping you reduce your consumption if you have that information at hand. But in electricity, water, and gas, and the resource side, well, what do we have? Well, we have these things called meters. Well, these meters are not designed for the end user. I mean, this is what the utilities look at to see how much they're going to charge you at the end of the month, right? And they're very hard to use. From an end user's perspective, they're just this ugly thing that's on the side of your home. But what do you really do with it? Also, they're pretty hard to find. This is a water meter, right? So after you do some digging, you might actually get to the water meter, right? And this was one of our participants' homes, right? You did a little bit of digging. Now maybe you can use the numbers here, if you know what they mean, to figure out how much water you're consuming before the end of the month bill comes in. So you can try to look at this thing to say, oh, how much water did I consume today? But it's really hard. I mean, this is a lot of work to actually figure out how much water you're consuming. They're also fairly esoteric numbers: kilowatt hours, CCF, gallons. What do I really do with those numbers? And so there's really not a good way to convey, or those things don't convey effectively to consumers about exactly what you're consuming. And even though there's been a lot of work in environmental psychology that has shown that disaggregated feedback, meaning just something as simple as an itemized bill, has shown reduction in overall consumption, sustained reduction of 15 to 20%, just by giving somebody an itemized bill. So the fact that you know exactly what appliance was running in your home and how much it consumed. So if I gave you a bill that showed you, here's all the appliances and electronic devices in your home, here's when they're run, and here's the relative distribution of their consumption, it can actually reduce consumption by 20% because you have that feedback that you can act upon. This is for electricity, water, and gas. But the challenge is how do you even do that? So Carl talked about a 100-home deployment. That was not easy. That was a very difficult deployment. So what we've been working on is ways that we can reduce the overhead of installing sensors that will give you that information. But before I talk about that, a lot of you might be wondering, well, why is residential space important? Isn't the big factory that's down the road the ones that really consuming a lot of water and electricity? Well, that's actually a misconception. It turns out that in the energy space, residential accounts for about a quarter of the energy used worldwide. In the water space, it's actually even more. More than half of our water is residential water. So this is actually treated water, so not agricultural. This is all pumped water that's treated at some point. But more than half is what we consume in our daily lives at home. So there's definitely a need, and we can actually make an impact by reducing our residential consumption. And so what we've been doing is building easy to deploy meaning non-expert installable. You're not going to call in a plumber, not an electrician. You're going to be able to install it yourself without any help. low cost, and high granularity, meaning that you get information down to each fixture or each faucet or each appliance, down to each device that you have in your home, and giving you an itemized feedback about that. And we're going to do it in such a way that it's going to give you an engaging and persuasive feedback. So it's not just going to be this bill that's just going to have a bunch of lines on it, but what are some interesting ways that we can present this information that's actually engaging? So both the sensing side and also coming up with effective feedback for presenting that data. And so, we've worked on 3 different projects: HydroSense, ElectroSense, and GasSense. Electricity, water, and gas. We've actually hit all 3 areas pretty aggressively recently. And so I'll go through each one of these to kind of give you an idea of what the kind of technology we're working on and what you might expect in the future. So before I go into that, if you wanted to build a system that gave you feedback down to each appliance, what would you do now? Well, right now what you would do is you would employ this notion of distributed direct sensing. What that would mean is, let's say you have an appliance. You want to know how much it consumes, how much power it consumes. You'd go out and buy a sensor. You can go to Target and buy one of these sensors. This is actually called a kilowatt. You can plug it in line with your appliance, and that'll give you appliance-level data, right? You can move this thing around if you want. You can install a couple of them. But this is one way of getting information about when a device is turned on and how much power it consumed. And so let's go into a kitchen. What would you do with this direct or distributed direct sensing approach? Well, I'd put one in the microwave. I want to see how much that's running. I'll put one near the coffee maker. I'll put one by the bean grinder. And the refrigerator, and all the lights, right? And so you can imagine how this actually doesn't scale that well. Even though these sensors are really cheap, the overhead of installing all these sensors is just too much of a barrier for anybody to actually go out and install it. So this is a major challenge, right? The retrofit problem is a major challenge, because we're not assuming smart meters. Smart meters won't even give you this resolution. Okay? Smart meters might just give you, maybe at the end of the month or at the end of the week, how much power you consume, but not at this level. So what we've been doing is looking at it from a different perspective. We're actually employing a very different sensing methodology, which is the idea of one sensor. You plug one device into your electrical outlet, and it gives you the same information that all of those sensors would give you, down to each appliance, or down the information about exactly which appliance is running and how long it's run. And the idea behind this is that if you think about the electricity, water, and gas infrastructure, each one of those are interconnected. It's basically a network that if you have electricity going from one place to the other, it's all one big system. So you can tap it at any place in that infrastructure. So let's just plug something in. And so what we've been doing is something very different. We've actually been monitoring the power line infrastructure, snooping it in such a way that we can figure out what electronic devices are being used by looking at the noise characteristics propagated by those devices. These are all electronic devices that have internal oscillators, internal components that are actually noisy, meaning that they're electrically noisy over the power line. And we've actually been able to figure out how to isolate that noise signature and tell you exactly which device got operated. If it was the TV, if it was the microwave, if it was the TV in the living room, or was it the TV in the bedroom, down to each different appliance in your home. And we do that by analyzing the noise signature. And you can do that with a single plug-in module. So this is something that an end user knows how to install. You plug this device into the wall, all right? Well, so this technology gives you what event happened. Did my refrigerator turn on? Did my light in the bedroom turn on? What device got turned on? We still need to get information about consumption. So how much power did this thing actually consume? And so the way you would do that now is you would open up your breaker panel. You would install these scary sensors called current transformers around the main lines coming in. Note that all of the metal is actually electrically hot. So being an electrician, I would actually be scared installing this, although this is the picture of me installing it here. So obviously an end user or non-expert would not install this, right? So this gives you power consumption. So what do? One sensor that's end user installable. So what we did was we built a non-contactless whole house power consumption sensor. This device, you literally peel the tape off the back. It has double-sided sticky tape, and you paste it on the outside of your breaker panel, something that you know where those switches are. And that gives you the same kind of data that this advanced current transformer-based solution gives you. It's actually more accurate than the off-the-shelf solution. It actually uses the magnetic field induced by the bus bar behind the actual panel to infer current consumption. And you can actually do this by just sticking it on the outside of the panel. So this has actually revolutionized how you can do whole house consumption by letting the end user install it. And so there's only 2 little LEDs there. The simple feedback is you hold it up against the panel, If it starts lighting up, you know you're in the right spot, you paste it right on there. So it's a simple stud finder-like model that people can use to install it. So what kind of things can we detect? We can detect everything, all right? So here's some examples. So the things on the top left, these are things that you might find in a kitchen. Well, this is interesting. Coffee maker, microwave, the oven got turned on. Well, what's interesting now is we can give you some even more interesting data about not just what turned on, but when it happened, right? Your cooking activities are now linked to these devices. So we can give you information about how much electricity does your cooking activities consume? How much water would your morning routines consume? So you can go down to that kind of level so you can give people consumption information, not just to individual devices, but their routines. Your cooking, your dinner activities consumes this much electricity. So now you can get people to get their head around exactly where the consumption is happening and how they can curb that a little bit. Something that's subtle here are things like refrigerator and microwave doors. You might be wondering, how do we get that? Well, it turns out when you open a fridge door or a microwave door, there's a light in there. The light has a switch. The switch has an electronic noise impulse that goes over the power line that we're able to detect. Something as subtle as a door light we can detect. So we can actually get very rich data about exactly what devices are being operated. So things like incandescent light bulbs, fluorescent light bulbs, all connected through a light switch we can detect. The most interesting things is that, let's say you have 200-watt light bulbs, one in the kitchen and one in the living room. Even though they might look exactly the same, they're 100 watts, but they're in two different locations, we can actually disaggregate those two based on the noise characteristics. So we've done something similar for water. So everybody always talks about electricity. Electricity, we got to solve the electricity problem. But water, I would actually argue, is the silent killer. Water, unlike electricity, is not a renewable resource. A lot of countries are actually importing water on barge ships. A lot of lakes are actually diminishing in the amount of water that they actually have. Atlanta was actually at a point where they only had 30 days of water left, right? So water is actually a very important consideration. So how can we do the same thing that we did in electricity for water? So the constraint is single sensor, no plumber, end user, non-expert installable. And so our technology actually does water inferencing down to each fixture, the toilet in the master bedroom or the toilet in the guest bedroom or bathroom. Is it the kitchen sink or is it the sink downstairs? And with a single sensor and how much water you're consuming at each one of those fixtures. Okay? So the way it works is really similar to the electricity model. There's some noise patterns that are propagated over the electricity infrastructure. Well, it turns out on the water infrastructure, there's the same thing. Well, here it's called water hammer. So every now and then you might turn on your water faucet and you hear this banging sound coming from your pipes. Well, that's because the impulse created by the activation of the valve creates a water impulse that goes throughout the entire infrastructure. And so it manifests itself as water hammer or this banging phenomenon. But if you're sensing it at one of the locations, you can actually sense it anywhere along the pipe. So where we install our sensor is, let's say a hose spigot. You know how to install a hose bib, a hose on a hose bib. So what we do is we screw it right on there. The next version will have a pass-through so you can continue to use it as normal, but you simply just screw it onto a hose bib. And the entire infrastructure is already interconnected. Even if we put this on the cold water spigot, we can still see hot water activities because of the hot water heater. It actually acts as a capacitor. It actually connects the two together. And so by sensing one location, we know what valve activities are occurring. If the toilet in the master bathroom went off, or was it the toilet downstairs that got flushed, based on the signatures that propagate from the valves that are actually in the home. And so we use our system to actually disaggregate that information. And so unlike a typical water meter you might find outside, in some parts of the country you might actually find it indoors if it's really cold. And so here, you would actually have to cut into the pipes and install a sensor. It would only give you aggregate information, whereas our sensor, HydroSense, screws onto a water spigot and gives you information that's down to each fixture. And so you can see how much value you can get from a technology that you can deploy yourself without having to hire a plumber. So we've been working in the gas space as well. So gas is actually even more interesting. Unlike electricity and water, there is no an analogy or equivalent of a plug-in device, right? Where do you plug in for the gas? Well, there's no plug-in. There's for obvious reasons, right? Gas is not a very safe resource, and so you definitely do not want the homeowner or the consumer cutting into gas pipes or trying to unscrew those pipes. So this actually makes it an even more interesting and harder challenge, but at the same time, there's very little technology out there to give you consumption down to which appliance is consuming how much gas. So I can't show you a slide for that because there is no cheap solution out there. So what we did was, well, we created one, a single sensor. So you notice a theme here, single plug-in modules, single screw-in modules, single devices. When my students come back to me and they say, I made 2 sensors, no, one sensor, right? So what we did for the gas technology was, well, what can we really interface with? We can't have them unscrewing hoses. We can't have them cutting into pipes. But it turns out that there's something really nice that's mandated by national code, which is a pressure regulator outside your gas meter. So when you go look at your gas meter, I'm sure everybody's going to look at it and look for that little disc. That disc on the left, top left, is a regulator that prevents transient spikes from occurring from both your home or from the actual feed coming in from the distribution center. And so what that allows you to do is to regulate how much pressure is going into the home. But it turns out that's a great place to put our sensor. So on the right, the black little disc there is literally a snap-on disc that goes onto the outside of the regulator. You just find where the regulator is, find where that tube is, and you clip it onto the edge. And what it does is it actually monitors the regulator to infer how much flow is going through the regulator and which fixture is being used. Again, there is a noise signature that manifests itself through the entire infrastructure that you can see at the regulator. And so we built the sensor and the signal processing algorithms to extract that information to tell you if it was your gas furnace, if it was your fireplace, gas stove, even which burner it was running. Was it the high power burner or the low power burner? All the way down to that level with a single sensor that you can install very safely. And so we've done a lot of in-home validations with this. One of the things that we pride ourselves in our lab is that we don't just do these things in the laboratory. We do in-home deployments. A lot of these technologies have been deployed in many, many homes where we've actually outfitted these homes, did ground truth sensing to make sure that the data we're getting from our sensors, how accurate is it? So the students often go into many different homes and deploy these technologies to see how accurate it is. So we've actually gotten a lot of field data for all of these technologies. And that's one of the value that we can get for this kind of technology is that it's so easy to deploy that we can do a bunch of homes simultaneously. So we've also been working on feedback applications. Now we have a very powerful sensing platform to allow us to quickly get data about consumption. Now we're looking at, well, how can we use this unique data set that we have and give homeowners and occupants information about their consumption? Now we have a whole test bed of sensors that we can use. So we can look at aesthetically pleasing interfaces, like, for example, this water interface here. What do we really need to show you? Do we need to show you every single device, or do we just need to give you the top 10 big consumers in your home? So we've been iterating on various designs on how do we actually present this effectively to the consumer. And so we're actually working on the interfaces and doing deployments with these interfaces to see, well, what is the right way of showing this data to the consumer? And doing this both in a way that you can see it at the end of the month or in real time. When you consume that resource, what does it look like then? So we're doing both real time and end of the month type feedback. Finally, a lot of this technology that we have been building is not just stuck in the lab. We're actually commercializing it. There's a very large commercialization effort going on that myself and my students are working on that's getting that technology out of the lab and actually into, eventually 250 million homes in the US. That's one of the things that we pride ourselves on as well, is we build innovative technology, build technology that makes a lot of difference in the research community, but also to the community at large. And so you've heard about Google Power Meter, Microsoft Home. All of these companies are going to eventually be leveraging this kind of data that we're building with our sensing platform. And you should stay tuned for this in the upcoming months. Finally, I want to conclude with not myself, but with my students. I have a fantastic group of students that I work with. It's the students that actually make this possible. This is the reason why I'm actually up here right now. So the other thing I want to mention is that I have a very diverse set of students I work with, all the way from computer science and engineering, electrical engineering, civil, and mechanical. So we have a very broad lab that we actually attack these problems with from many different angles. So we don't just look at this problem from a narrow perspective, all the way from the hardware to the environmental psychology and the end users and the interfaces for the technologies. The other thing to note is that we have students that are PhD students that are about to graduate, first, second year students. We have undergrads, freshmen. So there is a freshman on here that has already published 2 pieces of literature as a freshman on the technology that you've seen here. So that's the other thing we do. We get students in very early. And they love working on this technology because there's a socially meaningful application here, but they love doing the deployments and working on the technology. So are any of my students here? I want you guys to stand up. You got to stand up. Incidentally, so John Freilich is a senior PhD student. He couldn't make it here because he's actually on the East Coast in DC giving a talk at a behavior and climate change conference, probably very similar to the talk I just gave. And he actually ended the talk 3 hours ago. And so we've actually done very well in the community. A lot of people know about our work, and we're spreading the word very quickly now. Thank you.